Dear students, welcome to the knowledge series, and today we are going to discuss on classical relations and fuzzy relations. Now, as if you have gone through the video series with respect to the discussions on the extension principle, there I have elaborated about what exactly the extension principle or a fuzzy extension principle has to do with the two different sets and how that particular relation is existing between the two different sets. So here in this section we are going to see the sets of Cartesian's product, fuzzy relations, crisp relations. Now why this relation is so important? Because relation always represents the mapping of a two different discourse or a universe of a discourse. So there is a mathematical functions that exists between the two different discourse. So if the relation that is basically needed because it forms the connectivity in the logic. So based on that we carry on with the initial point of discussions with starting with the Cartesian product. Now here you can see that a fuzzy set A has a two elements 0 and 1. B is having an element A, B and C. Now when we do the Cartesian product, Cartesian is nothing but it's a perpendicular line that intersects the 2 points. So here I have shown a point where from the x and y, wherever it intersects, that particular point is termed as a Cartesian coordinate systems product. And here when we try to take a cross B, it's nothing but a relations of each element mapping to the other elements of the other set. So 0 to A, 0 to B, 0 to C. Similarly 1 to A, 1 to B, 1 C. That's how we represent here. Now similarly B cross A, then it will be A to 0, A to 1, B to 0, B to 1, C to 0, C to 1. That's all. And when we talk about A, then 0 and 0, 0 to 1, 1 to 0, and 0 to itself, 1 to itself. Similarly, B is have the similar form of 9 combinations. And when we try to take all this one and try to map in x and y coordinates, it will intersect at certain point. So here we try to take in the x-axis 3 elements 1, 2, 3, and y element A, B, C, and we try to show the coordinate diagram with respect to the relationship, that is the intersect point 1 and A, 2 and B, C, 3 and C intersecting at the one particular point, and we get something like a linear points. Now coming to the Cartesian product, one thing you have to understand: the Cartesian product of a two or a more set is not same thing as a arithmetical product of a two or more sets. That is one thing you have to keep it a Cartesian product, because it talks with respect to x and y coordinate points. So that's how we have to see that both are not same. Now coming to the crisp relations, crisp relations, it gives the relations with respect to the number of the A1, A2, A3, like different sets are being given, and each sets mapping with the another set, that is called as a array relations. So when we have a number of arrays, then the complexity of the relationship increases. So if array R is equal to 2, then in the two sets we can create that particular crisp relation in a easy manners. So Cartesian product of a two inverse of a discourse x and y, it is defined as all the element of x belongs to is subset of the inverse of a discourse, or belongs to the inverse of discourse x, and y belongs to the inverse of a discourse y, such that x belongs to capital X and y belongs to y. So we can represent here chi of x cos y. This is notations is chi, or you can for your easy understanding, is 1 and 0 if both the x and y is belongs to x cross cross y, and if it is 0 if it is does not belongs to x cross y. Now here one thing you have to know that x cross y is not same as y cross x. That is the relationship between the two universe of a discourse. So and mod of x cross y is mod of x cross mod y. Similarly, x cross y provides the mapping of the x belongs to x to y belongs to y. So that's the relationship that it determines. So that's how this particular mapping conditions between the two sets is being determined. Now here one thing you have to note that this particular equations which is being shown over here, this is a Cartesian product of a two universe. Now this particular relations x cross y is does not equal to y cross a. It is basically the constrained relations. Whenever these two mapping does not tally, then it is a constrained relations. Whereas in this particular case, it is a unconstrained relations that exist. So, the strength of the relations is completely related to if it satisfies the condition of x cross y is equal to 1 and 0 when x cross y does not belongs to subset. So this is the crisp relations, or we call it as a characteristic functions for representing these particular relations. Now coming to the next point is that we talk about a sagittal diagram for of the unconstrained relations. So that means there is no constraint. It's not like this. So when there is unconstrained, then there is a better mapping will be there. So here you try to see x is equal to 1 to 3, y is equal to ABC. You can try to see that there is a relationship exists between this one. So that's why the relation, it is denote in terms of a R. R column is that x is mapped to y. The relation is defined as x cross to y. So that is how we define this relation. And as I stated that this is a characteristic function in the to represent this particular terms. Now coming to the relations. Now let us see the relation matrix. Now relation matrix between the 1, 2 and 3 and ABC, it is equal to 1 when both the points are matching each other. Constraint relations means if 1 and 2 is there and A and B is there, only it map to a limited 1 to A, 2 to B, but there is no it does not state about the cross relations. So that is how we defined. So our if relations only restrict to this one, then we say that R is belongs to x cross y. So that is R is we can put it under the conditions that R belongs to a set x R cross y. Now coming to the universal relation and identity relations. Now universal relation and identity relations under this particular case, if you try to look across, I is equal to 0, 0, 1, 1, 2, 2. That is the your case with respect to the identity relations. And whereas universal relation is that it takes into consideration this identity relation as and also the relations with respect to the other sets also. So 0, 0 is there, you can see 1, 1 is there, 2, 2 is also there, and then 0, 1 is there, 0, 2 is there. Similarly 1, 0, 1, 2, then 2, 0, 2, 1. So this is all 9 combination you can try to see in the universal relations. So coming to the point with respect to these relations, there is an example given over here. Consider a two fuzzy set A and B given. A is given a set 1, 2, 3, 4, B is given 3, 5, 7, and a relation has to create. So all this one is a unconstrained relations. So you can have a mapping. So all the combination here is a 4 elements. Here is a 3 elements. So you can take a individual mapping with respect to this case. So you based on this you can have these sets of relations. So here it is mentioned that the relations case with respect to the R is equal to comma B, such that B is equal to A plus 1. B is equal to A plus 1 and comma A comma B belongs to A cross B. Now what does it means? That means these elements, these are nothing but the elements, and these are nothing but the sets. These elements belongs to these sets. Now if we take this condition that element A comma B such that B is equal to A plus 1, that means if you take any value 3, let us take a B is equal to 3, you will look for these relations among this. So 3, if I am taking 3 is equal to A plus 1, that means 1 plus 1, that is equal to 2. If that is the case, so any element which is having a 2, 3, so this you see, this element 2, 3, it satisfies these relations. So this that is 2 is this one and 3 is this one. Similarly, if you take a 5 you take here, no 5 is there. If you are taking A is, no, A is not having a, take 4 here, so this will become 5. So you will look for a 4 and 5. So this is another relation. So you can group this type of relations from the bigger sets. So this is what we talk with respect to the relations under the class of crisp relations. Now coming to the point of a crisp relations further, it is a subset of A cross B. Suppose A and B are two crisp set, then the Cartesian product is denoted by A cross B. Now this is what we term is that if A cross B is there, element belongs to that universe of a discourse A, B, or the elements belongs to that set A and B. So here it is the subset of A cross B. It is already stated, and here A and B are two crisp set. That means between the terms 0 and 1. Now the relationship of a particular it is already denoted by chi. So that is how we already stated in the earlier point, is that in the chi case, this particular relations, so the chi of x cross y of xy is equal to 1 when x and y belongs to this Cartesian product, and this one belongs to this Cartesian product. So the crisp relations, that's how we define the relations between 0 and comma and 1. So here I have put a 3 example relations between you and cousin, pressure and temperature relations, social problem relation. So all this relationship under unconstrained conditions will give a mapping to take a study. If it is a constrained one, then it has to look into that factor for a further study and how it has to resolve. Now the crisp relations case here is been shown with respect to the unconstrained conditions, and this is what been turned with respect to the with respect to the mapping, where the conditions satisfies the terms this one when it is equal to 1. Both are in the unconstrained conditions. Now coming to the point of a crisp relation, the strength is 0 and 1, and the fuzzy relations, it is between 0 and 1, where you will have a range of value between 0 and 1. Now coming to the fuzzy relations, I mentioned over here, fuzzy relations is having a relations not only the set element but also the membership value. so that the membership value will be having a range between 0 to 1. That is what being stated here. So you will be having a number of values x1, x2, x3. So this is known as tuples. So there are n tuples mean x1, x2, xn relations will exist. The strength of the relations is the order pair under these conditions, and the order pair of the two value and is not measured with the characteristic function but rather in the membership functions. Characteristic function always comes in the case of a crisp relations, but in the case of fuzzy relations we use the membership function to define, because based on the degree of the membership functions. Now if you look across the sagittal diagrams here with respect to the fuzzy relations x cross y, so we defines a set of element here x under the universe of discourse x and universe of discourse y, another x elements. So this is, if you are mapping a number of elements, then we say that if all the elements are mapping, then we say that this satisfies the conditions of the unconstrained. But if something is not mapping, then this is there is a difference in the difference between the two sets. So that difference put under the class of the constrained relations. Now binary relations referred as a bipartite graph. So that is what put across here. So this is a bipartite graph between the two relations under the case. But the previous we have seen the sagittal diagrams. So in the fuzzy relations, if the two relations put under the bipartite graph is been shown with respect to the number of arrows, number of joining points, and its membership functions. Now this binary again the binary relations with r x y, r x comma x, and r x square, that is known as a direct graph or a digraph. So that is represented in the figure over here. So in this particular sections, if you try to see across this one, if the particular x value is having a x square relations, so that is known as the symmetric relations. And if you find a relations like x1 to x2, then it is going back and you take these relations. Sorry, reflexive relation, anything across this one is known as a reflexive. But if x2 to x3 is one relations, x3 to x2 is another relations, that means one is 2, another is 4. So both these relation is known as symmetric relations. So that is known as a symmetric relations, and this is known as a reflexive relations. Now based on these reflexive relations and symmetric relations, we will be seeing a further study with respect to the fuzzy relations in the later part of the discussions, because this is one of the important point of the discussions with on the fuzzy relations topics. Now fuzzy relations with respect to the two fuzzy set, if you can put in the matrix form, that is the part and consists of all the membership functions. If x is having a relations x1, x2, xn, y is having a relation y1, y2 up to yn, then our fuzzy relations between x cross y we define in terms of a membership functions between these two, mu r of x1, y1, mu r of x1, y2, like that one. So this metric representations of the fuzzy relations is called as the fuzzy matrix. Now fuzzy relations mapping from a Cartesian space x cross y to the interval of a 0, 1, where the membership function is a order pair from the two universe of a mu r of xy. That means all this value, whatever we are selecting, it is going to be the selection based on the membership value that we defined in the unconstrained relations between the two sets. That will be coming over here. So if you talk about these relations, then it is going to come over here. That is what we see here for the discussions. Now coming further. Now if you look across these fuzzy relations, now fuzzy relations is a fuzzy set defined by the Cartesian product x1, x2 up to xn, where R, fuzzy set R, it is defined with respect to the x cross y, that is mapping to 0 and 1. So this 0 and 1 is 0, comma 1 is defined as the set of relations that defined with respect to the mapping of the two sets. Now, as we have seen here, there are the thing is that x1, x square the case, it is having a relations here. So under that particular case, it is a reflexive. Now here we try to see one is having a mapping with another, another is having mapping back to the. That means x1 to x2 and x3 is having a mutual relations. So that is known as symmetry. Now there is another is coming also. When everything is every relation is taken together, then that is known as a transitivity. So that is so one is reflexivity, second is symmetric, and third is nothing but a transitivity. So this is comes under the relation. Now here the relations between the two fuzzy sets is defined as x comma y, because we know that x comma y is that this is a two fuzzy set. If it is a single fuzzy set, we write x comma mu r of x. But since it is a two fuzzy set, so we have a and its relations we are taking. So that one comma mu r of x comma y. So this is the elements. This is the membership, such that x comma y, it's a subset of universe of discourse x cross y. So mu r of x comma y is the strength of the relation of a membership functions. Now here crisp set and fuzzy set is being shown. Now if you take a considerations of this particular representation of a graph, so A, B, C and D. So and here also A, B, C and D. Now here if you take a relation, it is represented in terms of a 1, and all other is reversed to reverse is 0. That means C to A, our relation C to A is 1, but relation between A to C is 0. So here if you try to say A to B, C to A, it is 0.8. So that's how we define. So here if you try to do represent in terms of a matrix, so we write ABCD here and ABCD here. So wherever the relation arrow is, say A to B, so A to B is 1, B to C, it is 1, C to D 1, C to A is 1, but if you take A to C, it is 0. Now here also you will find that only those relations which is having an arrow defines, that is how it will occupy, rest are 0. So this is a crisp relation, this is a fuzzy relations. So that's what we see here in this particular point. So we come to the point of discussions with respect to the fuzzy relations and its mapping, and with this we conclude over here, and by taking examples with respect to the Cartesian product, crisp relations and fuzzy relations. Thank you.